So at last you are only going to find, I think. Okay. Hi students, welcome to Future Doctor NEET Academy for the crash course, and this is NEET Physics crash course. Already we have completed 4 chapters. Today chapter 5, topic magnetism and matter. Some general properties of magnet. First to say what is magnet or what is magnetic substance. What are magnetic substance? What are magnetic substance?
To attract or
Yes, yes, yes. Substance which are attracted by a magnet are called magnetic substance. Okay. Can you say any example for magnetic substance? Magnetic substance example? Example for magnetic substance. Any one example? Yes, iron. Other example? Don't say another iron. Okay. That will keep as today's question. Not only iron, some more other substance, other metals especially, are also attracted by a magnet. That is, materials which are attracted by a magnet are called magnetic substance or magnetic materials. Okay, some general properties of magnet. First main property, magnets usually have 2 poles. That is, end of the magnet which points north when magnet is free to turn on a vertical axis. Then it's seeking north seeking pole, simply that is called north pole. That is okay. So that is this is what type of magnet this is? Can you name this what type of magnet? What's the name of this magnet? Bohr magnet. Is it so? It's a Bohr magnet. And here, when magnet is suspended freely using a thread, then what will happen? It may rotate freely, align freely, and north pole seeking towards the or pointing towards the north direction. That only we named it as north pole. Other end is a south pole. North pole seeking north side. Okay, that is a north seeking pole. And this is the basic thing to determine or to find or discover this thing. What is the name of this? Compass. What compass? Because we know the geometry compass. Is it any difference between this compass and geometry compass? Yes. This is a magnetic compass. Okay. This is a magnetic compass in which that needle, that magnetic needle, no, north pole, south pole. That's just like the Bohr magnet. And when it is kept freely, north pole pointing towards the north. So that only we called north seeking pole. And magnets usually have 2 poles. That is, single pole never exists. We can't say only north pole. That is, till now, any magnet, any small type of magnet if you take means, it contains 2 pole, north and south pole. There is no monopole. Mono means single pole. No single pole. If anything, any small, very, very small type of magnet if you take, it contains 2 pole, north and south. Okay. Next property. There's an explanation of this. The opposite end which points south is the south seeking pole or south pole. And magnets come in many shapes and sizes, but each has at least 2 poles. This only I explained. That is, if you divide this magnet into small, like this, cut into these 2, then this is north and here south. Again cut into off, cut into off. Even small piece of that magnetic piece also contain north one end and south other end. No monopole. That is, we can't find any piece of magnet, it contains only north or only south. Okay. And magnets come in many shapes and sizes, but each at least has 2 poles. That only I explained. This is the one type of magnet we will call as a horseshoe magnet, and this is just like bar magnet, and this and all other shape of magnets. This only I explain. If you cut a magnet into pieces, every piece will have still have at least 2 poles. Other property, like magnetic poles repel and unlike poles attract. Okay. What does the like magnetic poles mean? What is like magnetic poles?
North and north.
Yes. North with north or south with south. That is like poles. Like poles repel and unlike poles attract. So here south with south. What will happen? South with south, repel. North with north, like poles repel. South with north or north with south, it will attract. That only we said, like poles repel and unlike poles attract. A piece of magnetite. What is magnetite? What is magnetite? Come on. Magnetite is a ore of magnet. Okay, it is one of the ore of magnetic material. That is a magnetite. Okay, it is one of the ores of iron only. A piece of magnetite, when made to hang and swing freely, would align itself with the magnetic field of the earth following a north-south direction. That only we said in first point itself. That is north pole pointing north, south pole pointing south. So actually, what is the use of this? What is the main application? This main application is used to find the direction. In ships and all, we can find the direction. In ship and in aircraft, airspace there and all, this magnetic compass plays a vital role to determine or find the direction of the ships or airspace. Permanent magnets are magnets made from alloys of cobalt and nickel. Here is the question. The answer for this question. I asked one question, no. What is the other substance? Cobalt and nickel. Actually, iron, nickel and cobalt are the 3 magnetic substances. Okay. Iron is Fe and cobalt CO, nickel Ni. And mostly permanent magnets are made up of cobalt and nickel only. Okay. And these magnets retain their magnetism for a long time. That is why we are calling permanent magnet. Other metals like iron can be magnetized by induction. Induction means by giving some external, that is by giving electric current. At the time of passing electric current only, it retains magnetism. And when we switch off the electric field, it will lose its magnetism immediately. Best example, soft iron. When a piece of iron nails touches a permanent magnet, the nails become a magnet. And it retains this condition for as long as it within the magnetic field. And the nail is temporary magnet and its magnetism is described as induced magnetism. That is, induced magnetism means at the time of passing current only, it retains magnetism, it inducing magnetism, and when we remove the magnetic field, then it immediately loses the magnetism. That was we are calling as a temporary magnet or electromagnet. It's other name. Electromagnet or temporary magnet. Best example, iron, soft iron. And steel is a permanent magnet. And nickel cobalt is a permanent magnet. Actually, what is steel? Steel is an alloy of iron. Next, Coulomb's law. Coulomb's law or Coulomb's inverse square law. That is, force of attraction or repulsion between 2 magnetic poles. In first 2 chapters, we have discussed Coulomb's law in electrostatics. That is, force of attraction or repulsion between 2 charges. Now, force of attraction or repulsion between the 2 magnets, that only we are called as a 2 magnetic poles, is directly proportional to the product of their pole strength. That is, each magnet at the end, there will be a strength will be there, that we are calling magnetic strength as a pole strength. It is denoted by a symbol M. And each magnet force is product of the pole strength as M1 into M2. F is proportional to M1 into M2, that only product of the pole strength, and inversely proportional to R square, that is 1 by R square. This is 1 by R square. Okay, F is proportional to 1 by R square, or F is inversely proportional to R square. Then F equal to K into M1 into M2 by R square. Here K is a constant, just to remove the proportionality, and K is a constant, that value is mu naught by 4 pi. K is a constant equal to mu naught by 4 pi, and substitute this F equal to mu naught by 4 pi into M1 into M2 by R square. Okay, M1 into M2 by R square. And here mu naught, what is mu naught? Mu naught is called permeability of free space or vacuum. Its value is 4 pi into 10 power minus 1 T.M.A. power minus 1. T is a Tesla. And mu naught is a value is a 4 pi into 10 power minus 7 Henry per meter, or T m power minus 1 is a m a power minus 1. Its other unit is Henry per meter. Okay, Henry per meter is the other unit. Mostly this unit only used for mu naught. And in vector form, F equal to mu naught M1 M2 by R square by 4 pi, and we have introduced the R cap. What is R cap? R cap is the unit vector. R cap is the unit vector. What is unit vector? R cap equal to R cap equal to R vector divided by R, modulus R, or magnitude R, and that R only multiply with this R square as R cube. Therefore, F equal to mu naught into M1 into M2 by R square. So this is the formula for force. Force in Coulomb's law in magnetostatics or magnetism. This is the Coulomb's law in magnetism. F equal to mu naught by 4 pi into M1 into M2 into R vector by R square. Okay, your M1, M2 are the pole strength. What is the unit of pole strength? What is the unit of pole strength? Unit of pole strength is, you can write down, pole strength is Weber into meter. That is the unit of pole strength. Okay, M is a pole strength, its unit is Weber into meter. Okay, so this is the Coulomb's law in magnetism. Okay, I think students you noted, no? Can we move to next? Earth's magnetic field. A small Bohr magnet is said to have north and south poles, but is it more accurate to say it has a north-seeking pole and a south-seeking pole? By this expression, we mean that if such a magnet is used as a compass, one end will seek or point to the geographical north pole of the earth, and the other end will seek or point to the geographical south pole of earth. Geographical south pole means for earth is a north pole, south pole. That only we are calling geographical north, geographical south. Okay, and that Bohr magnet only modified into compass or magnetic compass needle. Okay. And we therefore conclude that the geographical north pole of earth corresponds to magnetic south pole, and the geographic south pole of earth corresponds to magnetic north pole. This I will explain. This is the earth. Okay, and earth, suppose earth total magnetic field will be at the center, and it behaves like a magnet, and actually magnetism present in the earth will be, this is actual north, this is actual our north. Okay, and the south pole of earth's magnet is in north side, and north pole of earth's magnet is in south side. That's why if we suspend a Bohr magnet here, north and south will attract. Okay, suppose if you suspend the suppose this is a bar magnet as north pole, south pole. We suspend that freely and it align, how it will be aligned? It will be aligned like this only. Is it so? North and south. That is, north and south only will be attracted and south and north attract. That's why north pole seeking towards the north direction. Okay. So, earth itself behave as a huge magnet in which south pole of that earth magnet is pointing towards the geographical north. This is a geographical north. And north pole of earth magnet pointing towards the geographical south. Clear? That is why north pole attracts south and south pole attracts north. That's why it can seek easily or pointed towards the north pole pointing towards north, south pole pointing towards south. Okay. This is the reason for Earth's magnetic field. Next, horizontal component of Earth's magnetic field is denoted by a symbol BH. The total intensity of the Earth's magnetic field does not lie in any horizontal plane. Instead, it lies along the direction at an angle of dip, delta to the horizontal. Delta, that is called angle of dip. The component of Earth's magnetic field along the horizontal at an angle delta is called horizontal component of Earth's magnetic field. That is denoted by symbol BH. And BH equal to B cos del. And similarly, vertical component B sin del. Okay, BH equal to B cos del and BV equal to B sin del. Actually, cos del equal to B by BH will come cos del equal to B by BH. Cos del equal to. Then B equal to BH cos del. Oh, sorry. Actually, no. Wait. Cos del equal to BH by BS. BH by B. Cos del equal to BH by B, then BH equal to B cos del. Or we can say this BH is resolved into two component as this B is resolved into two component as B cos del. This will be B cos del. And this is B sin del. As horizontal component, vertical component. B cos del is the horizontal component, B sin del is a vertical component. And tangent law. If a magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular to each other, the needle will align itself along the direction of resultant field of the two fields at an angle theta, such that tangent of the angle is the ratio of the two fields. That is tan theta equal to B2 by B1. Tan theta equal to B2 by B1. This is the tangent law. Okay, tan theta equal to B2 by B1 and B2 we can say as B sin del and B1 is B cos del. Okay. No. Can we move to the next topic? Magnetic materials tend to point in the north-south direction. This we discussed. Like magnetic poles repel and unlike ones attract. Magnetic poles cannot be isolated. Cannot be isolated means, what is isolated meaning? We can't separate north pole and south pole. You take north pole, I will take south pole, like that we can't keep. Okay, if you divide any small type of magnetic material, it contains both north and south. That only monopoles not exist or magnetic poles cannot be isolated. Isolated means we can't separate north and south. When a Bohr magnet of dipole moment M is placed in a uniform magnetic field B, then the force on it is 0. Then the torque in it is M cross B, that is tau equal to M cross B. Okay, M cross B. and its potential energy U equal to minus M dot B. Okay, tau is a torque or magnetic moment, turning effect of the force equal to M cross B, and U equal to minus M dot B. And here we choose the zero of energy at the orientation where M is perpendicular to B. And this is the formula, tau equal to M cross B. Torque is the turning effect of the force. U is the potential energy equal to M dot B. Okay. Okay, can we move to next? You noted, or I want to show this? Noted, no? Okay. Consider a Bohr magnet of size L and magnetic moment M at a distance R from its midpoint. Here R is very greater than L. Then the magnetic field B due to this Bohr magnet is B equal to mu naught M by 2 pi R cube along axial line. Just like in electric field we have discussed, no? That is a two dipole moment, that is two dipoles will be there, plus Q and minus Q separated by 2d distance, and we found the electric field at the point when it is in the axial line. Some formula we derived, and the point is at the equatorial line. Same here, instead of plus Q and minus Q, here M. Okay, pole strength M, magnetic pole for north side and south side, and when the point is at here, that is along the axial line. When the point is at here, equatorial line, this will be equatorial line at P1, P2. Then magnetic field B equal to mu naught M by 2 pi R cube. This is along axis, that is when the point is at axial line. And same way, B equal to mu naught M by 4 pi R cube when the point is along equatorial line, that is point P2. Okay, at P2 it's like this. Clear? As one side north, another one south, and distance 2d. Okay. Gauss law for magnetism. Whatever in electrostatics, same thing will be repeated in magnetism. It states that net magnetic flux, there we used electric flux phi or phi of E. Phi is electric flux. Okay. Same way, phi B means magnetic flux. Magnetic flux phi B equal to sigma B dot delta S into equal to 0. Just like there what we discussed, phi equal to what is the formula for Gauss law? 1 by epsilon naught times of sigma Q. 1 by epsilon times of summation of charge or net charge enclosed in the surface. That is Gauss law. Same way here, net magnetic flux through any closed surface is equal to 0 here. That is B dot delta S equal to 0. There E dot delta S equal to 0, that is equal to these things. Okay. This is a Gauss law in magnetism. Okay. The pole near the geographical north pole of the earth is called the north magnetic pole, and pole near the geographical south pole is called south magnetic pole. And the magnitude of magnetic field on the earth's surface is equal to 4 into 10 power minus 5 Tesla. Actually, I don't know present plus 2 students, they found that BH of the earth, that is using tangent galvanometer, they found, I think, in physics laboratory in 12th standard. They are studying is important lab practical tangent galvanometer. In that they are finding the BH of the earth. BH is the horizontal component of earth's magnetic field. Its exact value is 3.8 into 10 power minus 5 Tesla. This is only given as approximate value, 4 into 10 power minus 5 Tesla. Horizontal component of Earth's magnetic field, BH. Using tangent galvanometer, there is the experiment is there, one formula is there, and students observed the reading. I myself, when I was teaching in +2, I myself taught this one, but I don't know in present year is there or not. Have you studied that one or not? Tangent galvanometer, theory you studied, I think. Theory you studied. Oh, deleted topic. Okay. Theory you studied. In practical, no. Okay. At that time, this is an important practical lab, physics lab. In that, students are able to find the value of 3.8 into 10 power minus 5 Tesla. This is only approximately given as 4 into 10 power minus 5 Tesla. This is the horizontal component of Earth's magnetic field. Okay. And elements of Earth's magnetic field. 3 quantities are needed to specify the magnetic field of the Earth on its surface. First one, horizontal component. This only BH we gave. We said as BH. So, BH. And magnetic declination and magnetic dip. These are the 3 important Earth's magnetic elements. And these are known as the elements of Earth's magnetic field. Magnetic intensity. Consider a material placed in an external magnetic field B0. The magnetic intensity is H equal to B0 by mu naught. B0 is the external magnetic field, mu naught is the, what is mu naught? Permeability of a free space or vacuum. And if the magnetization M of the material is its dipole moment per unit volume, then the magnetic field B is B equal to mu naught into H plus M. H is the magnetic field strength, that only equal to B naught by mu naught. H equal to B naught by mu naught, and B equal to mu naught into H plus M. M is the magnetization or intensity of magnetization. Its other name, intensity of magnetization, is also denoted by a symbol I. I or M is the intensity of magnetization. For that, what is the formula? Intensity of magnetization is nothing but magnetic moment per unit volume, that only given here. Okay, intensity of magnetization is the magnetic moment per unit volume. Then, for a linear material, magnetic moment equal to chi into H. What is this? This is called chi. It should be read as chi, and then it is called magnetic susceptibility. Here chi is called magnetic susceptibility. Then here M equal to chi into H and B equal to mu into H. Actually, what is chi means? Chi equal to I by H. That is the formula for chi. Chi is the susceptibility. Magnetic susceptibility is chi. Okay. And chi is the magnetic susceptibility, and mu r is the relative magnetic permeability. That is next, that is we are going to find the relation between mu r and mu. That is magnetic permeability, mu is related as mu equal to mu naught into mu r. Just like in electrostatic we studied, no, epsilon equal to epsilon naught into epsilon r. Just like that here, mu equal to mu naught into mu r. Here mu r is only a relative permeability. Mu r is the relative permeability, and mu r equal to 1 plus chi is an important relationship between relative permeability and susceptibility. Relative permeability and susceptibility is not given by a relation mu r equal to 1 plus chi, or chi equal to how much? 1 minus mu r or mu r minus 1 from this formula. 1 minus mu r. Chi equal to 1, if it goes there, becomes minus 1. So, mu r minus 1. Okay. Chi is be as it is. 1, if it goes this side, become minus 1. So, mu r minus 1. Chi equal to mu r minus 1 or mu r equal to 1 plus chi. Okay. Let's move to next topic. Classification of magnetic materials. Based on the magnetism present or how it behaves in the magnetic field, magnetic lines of force, materials are broadly classified as diamagnetic substance, paramagnetic material or ferromagnetic material. Okay, so it's three types: diamagnetic material, paramagnetic material, and ferromagnetic material. Ferromagnetic material, they are in solid state. All the ferromagnetic material are solid state material only. What is the example for ferromagnetic material? That we'll discuss. And paramagnetic material, they can be solid, liquid, or gas. Paramagnetic material may be solid or liquid or even gas. Diamagnetic material can be solid, liquid, or gas only. Effect of magnet: strongly attracted by a magnet. Okay, ferromagnetic material are strongly attracted by a magnet. Paramagnetic material weakly attracted by a magnet. Diamagnetic material weakly repelled by a magnet. Weakly will be used by a word feebly. Feebly means slightly or weakly. Okay, strongly attracted by a magnet, and paramagnetic material feebly attracted by a magnet. Diamagnetic material feebly repelled by a magnet. Effect of magnetism: and behavior under non-uniform magnetic field tend to move from low to high field region. When this ferromagnetic material is kept in the non-uniform magnetic field, then it starts to move from low magnetic field to high magnetic field. That is the behavior of ferromagnetic material. Paramagnetic material move from low to high field, this also. And diamagnetic material reverse. It moves from high to low field region. Moves from high field to low field region. And para and ferro same. Moves from low field region to high field region. Behavior under external magnetic field: they preserve the magnetic properties after the external field is removed. Okay, it can preserve the magnetic properties after the external field is removed. That's why we are calling this a permanent magnet. And they do not preserve the magnetic properties once the external field is removed. Diamagnetic material, they do not preserve the magnetic properties once the external field. Both are not preserving. Okay, not behaving, only at the time of passing magnetic field only it behaves the or retains the magnetism. Okay. Effect of temperature: ferromagnetic material above Curie point or Curie temperature, it becomes paramagnetic. That is, there is a ferromagnetic material, and if you heat the material, if you increase the temperature of the material, then there is a one particular temperature for each ferromagnetic material. When it reaches that point, then ferromagnetic material is converted into paramagnetic material. So that is the actual definition for Curie temperature. What is Curie temperature? Curie temperature is the temperature in which ferromagnetic material can be converted into paramagnetic material. Same way for paramagnetic material, with the rise of temperature, it becomes diamagnetic. There we will use a word critical temperature. The temperature is called critical temperature. So at this temperature, paramagnetic material is converted into diamagnetic material. Diamagnetic material, no effect. When temperature increases or decreases, no change in the behavior. That is a diamagnetic material. So diamagnetic material is independent of the temperature. Permeability. Permeability value is very high for ferromagnetic material. And for paramagnetic material, greater than unity. This value will be very, very greater than 1. Mu r is very, very greater than 1. Here this value is mu r is greater than 1 slightly. And here mu r is less than 1. Okay. And susceptibility. What is the symbol for susceptibility? Chi. Susceptibility value is very high and positive. This value is high value and positive. It is just greater, positive, but greater than unity. Chi value is just greater than unity. And little but less than unity, and here chi value is negative value. And both are here positive value. This also positive, this also positive. Example: iron, nickel, cobalt. Already we said these three only magnetic substance. Iron, nickel, cobalt are the best example for ferromagnetic material. Paramagnetic material: platinum, aluminum, chromium, manganese, sodium, nickel. Diamagnetic substance: copper, silver, gold, mercury, and another important one, superconducting metals or superconducting material. Have you studied superconducting material in your plus 2? Superconducting substance or superconducting material or superconductor, studied or not? I think in state board is there, superconductor. So superconducting material is a diamagnetic material. Okay. What are superconductor? It behaves the diamagnetism, it retains magnetism as a diamagnetic material. Definition for superconductor. Superconductors are the material which, that is, whose resistivity is 0 or conductivity is infinite. But it acts as a superconductor only at low temperature. Superconductor is the material whose conductivity is infinite conductivity or 0 resistivity at very low temperature are called superconductor. Best example for main application for superconductor is bullet train. Bullet train, no, in Japanese recorded that fastest train around 500 plus kilometer per hour. That's based on superconducting material only. Okay. Okay. So chapter 5 over. Let's move to chapter 6, electromagnetic induction. Chapter 6, electromagnetic induction. As we have discussed already, we are concentrating first in theory for crash course and then problem we will do. Okay. Electromagnetic induction. Voltage is induced whether the magnetic field of a magnet moves near a stationary conductor or the conductor moves in a stationary magnetic field. See, this is the coil, there is a wire. Wait. So this is a wire connected with the galvanometer or ammeter, and magnet is bringing near that. Then what will happen? Deflection will take place. So by changing the magnetic flux or magnetic field, then some amount of voltage is induced. That is only electromagnetic induction. Using the magnet, electric field is induced. Using the magnetic field, changing the magnetic flux linked with the coil, then electric current is induced in it. This is called electromagnetic induction, or this phenomenon is called electromagnetic induction. And here magnetic flux through a plane of area dA placed in a uniform magnetic field B, phi equal to integral B dot dA. Actually here B equal to phi by A. Okay. B is a magnetic induction or magnetic field, phi is the magnetic flux, A is the area, and phi is the total flux or total magnetic lines of force. Total magnetic lines of force per unit area only B. Then B equal to means from this B equal to phi dot A. Oh sorry, phi equal to B dot A. Okay. So phi equal to B dot A. That only given. And phi equal to integral of B dot dA. And this is the plane of the paper, and this is the magnetic field direction. dA is the perpendicular to the area, perpendicular to the plane of paper. And theta is the angle between the direction of magnetic field and perpendicular to the plane of the coil. That is only theta. Okay, theta is the angle between the direction of magnetic field and perpendicular to the plane of a coil. And B dot dA or B dot dA or BA cos theta. Integral B A cos theta, because A dot B equal to AB cos theta. That's the formula. A dot B equal to AB cos theta. Okay. Faraday's law. Faraday's first law states that whenever there is a change in the magnetic flux linked with the circuit with time, and EMF is produced in the circuit which lasts as long as the change in magnetic flux continues. That is Faraday's first law. Whenever there is a change in magnetic flux links with the circuit with time changes, and EMF is produced in the circuit which lasts as long as there is a change in flux continue. Whenever there is a change in flux continues, then only EMF is induced. This only I showed in first this one. When magnet is moved there, then magnetic flux linked with the coil will be changing. Whenever there is a change, deflection will be produced. If deflection is there, current is flowing. It produces some current. Okay. So that only electromagnetic induction, and here is the Faraday's first law. That is, whenever there is a change in magnetic flux links with the circuit, and EMF is produced in the circuit which lost means which exists as long as the change in magnetic flux continues. This is Faraday's first law. And Faraday's second law. According to this law, induced EMF is proportional to d phi by dt is nothing but rate of change of magnetic flux. Induced EMF is directly proportional to rate of change of magnetic flux. Rate of change of magnetic flux. That is only equal to induced EMF. E is proportional to d phi by dt, or E equal to d phi by dt. Okay. E equal to d phi by dt. This is a demo. Induced voltage in a coil is proportional product of number of loops and rate at which the magnetic field changes. How fast it's moving. Suppose this magnet is moved very fast or very slow. So that is a slowly if you move means small voltage is produced. Fast if you move means high voltage is produced. Another one, number of turns of coil. Here it contains few turns of coil, very few turn, and number of turns is increased. Large number of turn, what will happen? Large voltage. So it depends upon the number of turns of coil also. So E equal to d phi by dt we said. Okay, and this phi depends upon n number of turns of coil also. It depends upon number of turns of coil. If number of turns of coil is more, then EMF induced also more. Okay, see, 2 turns only, very small voltage. Some 4 or 5 turns, medium voltage. Large number of turns of coil, large voltage is produced. Lenz's law. Direction of induced EMF or current in the circuit is such that it opposes the cause due to which it is produced. So that E equal to minus n into d phi by dt. E equal to minus n into d phi by dt. Here negative sign indicates it opposes the cause. That only negative sign. Suppose it does not oppose the cause means it will be done automatically. By like that it will not act. So that is opposes the cause is given by a negative sign. Okay, negative sign is indicates that it opposes the cause. And here n is the number of turns of coil, and Lenz's law is based on the energy conservation. It is based on the energy conservation. That is how is the energy conservation. Magnetic energy is converted into electrical energy, or magnetic energy stored in the magnetic form that only converted into electrical energy form, like that. That is a conservation of energy. And this is the Lenz's law. Metal ring is levitated by self-induced secondary magnetic field, and here due to that connected to this, and it opposes the cause in this. For the demo, Lenz's law demo is this one. And induced EMF and induced current. Induced EMF E equal to minus n into d phi by dt, or this is equal to minus n into phi 2 minus phi 1 by t. Then induced current I equal to E by R. That is, we know the relation between I and E as from Ohm's law. E equal to or V equal to IR or RI. From that, I equal to E by R. And substitute the E value as n into phi 2. D phi is nothing but phi 2 minus phi 1. Change in flux. d phi is phi 2 minus phi 1 with respect to time. Then substitute this here, then E by R. Substituting for E equal to N by R into d phi by dt. And as we said, d phi is nothing but phi 2 minus phi 1 by t, and charge depends only on net change in flux and does not depends on time. Okay, this charge depends on net change in flux only and does not depends on time. That is the induced current formula. Okay. Can we move to the next topic? Induced EMF due to linear motion of a conducting rod in a uniform magnetic field. Induced EMF E equal to minus L into V cross B. Okay. Induced EMF E equal to minus L into V cross B, or E, V and B are perpendicular to each other. Then E equal to B, V, L. B is a magnetic field, V is the velocity, and L is the length of the conducting rod. E equal to B, V, L. Induced EMF due to rotation of a conducting rod in a uniform magnetic field. E equal to half into B omega L square, and omega equal to 2 pi into N. N is a frequency, that only B pi N into L square, and A equal to L square. A equal to L square, area. And induced EMF due to rotation of a metallic disc in a uniform magnetic field of B omega R square. Instead of L, R we use, that's all. Instead of L, R. So B omega R square equal to B pi R square N, or here pi R square. Oh, here A equal to pi L square. Pi L square. A equal to pi L square, and here A equal to pi R square. Because rod means conducting rod. Rod is a cylindrical shape and circular cross section. Area of cross section of a rod is circular cross section. So A pi L square or A pi R square. A equal to pi R square. Okay. Then induced EMF, current and energy conservation in the rectangular loop moving in a non-uniform magnetic field with a constant velocity. Net increase in flux, del phi equal to B2 minus B1 into L into V into del T. That is del phi by dt equal to B2 minus B1 into LV. Del phi means into del T. And induced EMF in the coil is E equal to B1 minus B2 into LV. That is E equal to phi by T. From this, del phi by del T equal to B2 minus B1 into LV, and del phi by del T is equal to E. So E equal to B1 minus B2 into LV. And in terms of induced current, I equal to E by R equal to B1 minus B2 by R into LV. And resultant force F equal to BIL formula we know. If you substitute this, F equal to IL into B1 minus B2. F equal to IL into B1 minus B2. And your work done is against the resultant force. Can we move to next? Rotation of rectangular coil in a uniform magnetic field. Magnetic flux linked with the coil phi equal to BAN cos theta. BNA cos theta. B is the magnetic field, A is the area, N is the number of turns of coil into cos theta. Theta is the orientation of a coil. And theta equal to omega t. Omega is the angular frequency, theta equal to omega t if you substitute, phi equal to BAN cos omega t, and induced EMF in the coil E equal to d phi by dt. This is from Faraday's law. And if you substitute this here, BAN omega sin omega t, and this BAN omega is equal to E naught. Let E naught equal to BAN omega. Then E equal to E naught sin omega t, simplified formula. E equal to E naught sin omega t. And induced current in the coil I equal to E by R, substituting this BAN omega by R sin omega t, and BAN omega equal to E naught B star. So I equal to E naught by R sin omega t. I equal to E naught by R sin omega t. Both EMF and alternating current in the coil are alternating with respect to time. Okay. Alternating with time. Next is self-induction and self-inductance. The phenomenon in which an induced EMF is produced by changing the current in a coil is called self-induction. The phenomenon in which an induced EMF is produced by changing the current in a coil is called self-induction. That is, change in the magnetic flux in one coil, in a coil, and induced EMF also in the same coil, then we are calling self-induction. And phi is proportional to I. What is phi? Phi is a magnetic flux, I is the current. When current increases, phi also increases. And by removing proportionality, there is a constant, that constant is L. By removing proportionality, there is a constant, that constant is L. Phi equal to L into I. Phi is proportional to I, or phi equal to L into I, or L equal to phi by I. L equal to phi by I. Then E equal to minus L into di by dt. Okay, E equal to minus L into di by dt. Then L equal to E divided by, if you simplify this for L equal to E by minus di by dt. Using this, we will work out some problems and all in this chapter afterwards. Okay. So E equal to minus L into di by dt, or L equal to E divided by minus di by dt. Here L is a constant called self-inductance or coefficient of self-inductance. Okay. L is a constant called self-inductance or coefficient of self-induction. Self-inductance of a circular coil L equal to, in terms of mu naught n square pi r by 2. Mu naught n square pi r by 2. And in this, multiply and divided by r. In this formula, multiply and divided by r, then pi r square is A equal to pi r square and 2r, that only this formula. Okay, mu naught n square pi r by 2, multiply and divided by r, then pi into r, pi r square equal to A divided by 2r. And self-inductance of a solenoid L equal to mu naught n square A by L. Self-inductance of a solenoid L equal to mu naught n square A by L. And two coils of self-inductance when it is connected in series and parallel, just like resistance connected in series parallel, capacitance connected in series parallel, inductance when connected in series. L equal to L1 plus L2 plus up to Ln is same like our capacitor. Capacitor, resistor? Resistor. Resistor only when in series R equal to R1 plus R2 plus R3. In capacitor it is different, opposite. So for series combination L equal to L1 plus L2 plus L3 up to Ln, n number of capacitor. For parallel combination, reciprocal 1 by L equal to 1 by L1 plus 1 by L2 plus up to 1 by Ln. This is for inductors when it is connected parallel. Okay. Inductance when it is connected in series is, this is a circuit symbol for inductance as L1, L2, L3. This is connected in series, and parallel L1, L2, and this is for parallel L1, L2, L3. Okay, connected in parallel. Just like self-induction, mutual inductance. On changing the current in one coil, if the magnetic flux linked with the second coil changes in the neighboring coil, that is called mutual inductance. That is, on changing the current in one coil, the magnetic flux linked with the second coil changes. Magnetic flux linked with the second coil changes. That is a P is we are calling primary coil, and here if the current in the coil changes, if there is a change in the current in the coil, then magnetic flux linked with the secondary coil changes and it induces the EMF that will be shown in the galvanometer deflection. That is called mutual inductance. That is, current in the one coil, primary coil changes, then magnetic flux linked with the second coil that we are calling secondary coil changes and it induces EMF. That is called mutual inductance. Phi 2 is proportional to I1. I1 is the current flows in the primary circuit, and here phi 2 is the magnetic flux in the secondary circuit. Phi 2 is proportional to I1, or phi 2 equal to M into I1. Phi 2 equal to M into I1. Here M is the mutual inductance. M equal to phi 2 by I1, or E2 equal to minus d phi 2 by dt, and substituting this minus M into di1 by dt. Okay, that is from this phi 2 means phi 2 equal to M into I1, and substituting this phi 2 equal to M into I1 here, M is a constant, take out of differentiation, minus M into di1 by dt. Then E2 equal to minus M into di1 by dt, then M equal to E2 by minus di1 by dt. And here M12 equal to M21, that can be simply M. Okay, M12 is the mutual inductance of 1 with second coil, or M21 2 with first coil, that is equal to M. All are same, so just denoted as just M. Mutual inductance for two coaxial solenoids. M equal to mu naught N1 N2 A by L. N1 is the number of turns in primary coil, N2 is the number of turns in the secondary coil. A area, L length. And if two coils of self-inductance L1 and L2 are wound over each other, then mutual inductance M equal to K into square root of L1 L2. This formula gives a relationship between mutual inductance and self-inductance. Okay, it gives the relation between mutual inductance and self-inductance. M equal to K into square root of L1 into L2. Here K is called coupling constant. K is called coupling constant. Next, mutual inductance for two coils wound in same direction and connected in series. L equal to L1 plus L2 plus 2M when it is connected in series. When it is connected in series but wound in opposite direction means L equal to L1 plus L2 minus 2M. And mutual inductance for two coils when it is connected in parallel. L equal to L1 into L2 minus M square divided by L1 plus L2 plus or minus 2M. This is for parallel. And these two is for series. Series, that two coils wound in same direction and these two coils wound in opposite direction. Okay. Next, energy stored in inductor. Energy stored is the potential energy which is stored in the form of magnetism. UB equal to half into Li square max. Energy stored is potential energy. UB equal to 1 by 2 Li square max. And magnetic energy density UB equal to B square by 2 mu naught. B square by 2 mu naught. Eddy current. When a conductor is moved in a magnetic field, induced currents are generated in the whole volume of the conductor. When a conductor is moved in a magnetic field, induced currents are generated in the entire volume of the material. These currents are called eddy currents. Okay, that current is called eddy currents. Okay, can we move to next? This we discussed. Change in magnetic field induces eddy current within any conductor. So that change in magnetic field takes place in the entire material. Transformer. Transformer is a device which changes the magnitude of alternating voltage or current. Here ES is the EMF in the secondary, EP is the EMF in the primary, and NS is the number of turns in secondary, NP is the number of turns in primary, and equal to K, one constant K. For ideal transformer, IP by IS equal to NS by NP. Some place we may use capital N also as NS by NP. IP by IS equal to NS by NP. In an ideal transformer, EP into IP equal to ES into IS. What is EP? EP is the EMF induced in the primary. IP, current flows in primary. ES is the EMF induced in the secondary. IS, current flows in the secondary. In step-up transformer, number of turns in secondary is greater than number of turns in primary. Or now ES is greater than EP. EMF in secondary is greater than EMF in primary. And E and I are in reverse. N and E same. Okay. See, ES is greater than EP means here IS is less than IP. Opposite. What is step-up transformer? Step-up transformer is a device which convert low voltage to high voltage or high voltage to low. Step-up means low to high. Low voltage to high voltage, that is step-up transformer. Step-down transformer, high voltage to low. Here NS is less than NP or ES is less than EP and IS is greater than IP. And efficiency eta equal to ES into IS by EP into IP into 100%. Efficiency eta equal to ES into IS by EP into IP into 100%. It's denoted by a symbol eta. Generator or dynamo, this will be a last topic. Device, it is a device by which mechanical energy is converted into electrical energy. It is based on the principle of electromagnetic induction. What is generator? It converts mechanical energy to electrical energy. Different types of transformer. AC generator, it consists of field magnet, armature, slip ring and brushes. DC generator, slip ring is replaced by split ring or commutator, and all the other things are same, that is for DC generator. And this is the construction of AC generator, 2 bar magnets, and this is a coil we are calling armature, and here brushes, carbon brushes and split rings, and alternating current can be drawn here only. You can draw alternating current here. And this is the circuit symbol for alternating current as sinusoidal voltage, same as the sine wave. And here how is it? When time increases, then E value increases and decreases and increases and decreases in opposite direction. That is AC. What is alternating current? We discussed already in electric current or current electricity. That is, current value or EMF value changes continuously with respect to time, and also the direction changes periodically. That is the alternating current. Motor is a reverse form. Motor is converts electrical energy into mechanical energy. Here E is proportional to the omega, and its efficiency is equal to EB by E into 100%. Motor is a reverse process of generator. Current flowing in the coil E equal to EB plus IAR, and efficiency you can note down. Just write down the definition of motor and then efficiency. Efficiency eta equal to EB by E into 100%. Definition: device which converts electric energy into mechanical energy. Efficiency eta equal to EB by E into 100%. Okay.